So today in the physics department seminars, we're having Professor Piers Coleman. He's a professor on Rutgers University in the USA, but also recently he's a part-time or half-time professor also in the University of London. Professor Coleman, he made his first studies in Cambridge in the UK. Then he moved to Princeton to make the PhD. Then also a postdoc, he was postdoc at the Santa Barbara. And I understand that you returned then to Cambridge. And finally, you got the position at the Rutgers University.
That's right.
Where he has been working since 1987. He's very well known for his contributions in condensed matter, and especially in strongly correlated electron systems. And probably most of you know him for his book, Introduction to Many Body Physics. And I asked him to give a broad talk on these challenges on solid-state physics today. So please.
Thank you, Rodrigo. Yeah, okay. Well, I'll get going. It's a delight, but also great sadness that I'm giving a talk to you by Zoom. I've never been west of the Andes in South America, and I miss coming down. I've often been to Brazil, and I miss coming down to South America. So, you know, in another world, I would have loved to have been there physically with you guys. Anyway, so today I'm going to give you a colloquium talking about some of the challenges of the solid state. And I called it provocatively, as Rodrigo said, dark matter challenges of the solid state. I'd like to encourage you to ask questions, not just at the end of the talk, but to interrupt me, because I think it's much more fun to have a dialogue than to just zoom through slides. And I probably won't get through everything in my talk anyway, and that doesn't matter. Let's see if this is going to work. Come on. Okay, so let's go to the next slide. Yeah, come on. So the work I'm going to talk about today is not only my own work, and it really contains contributions from a broad range of people, from postdocs who have now gone on to junior faculty positions, my longtime collaborators, Alexei Svelik, Premi Chandra, my partner at Rutgers, and also a whole bunch of experimentalists down here. They're not all experimentalists. Centil is not a set experiment, but the other ones are, who have kept me honest along the time. Anyway, so let's move on. And this is an outline of my talk. Let's see how far we get. This is a colloquium, so you'll forgive me for reminding us all of what we already know. I think that's an important part of reflecting on the state of our science today. So I'm going to talk about early signs of the quantum age, and I'm going to do that in part because today we find ourselves once again at a precipice of understanding, and I want everyone to reflect on the fact that physics is potentially at the edge of another revolution. One other thing I will talk about, I will spend a lot of time talking about emergence and reductionism. We know today that science isn't just a question of finding the laws of the smallest parts, but also understanding how it all comes back together again. And sometimes we need to understand the emergent properties of a system to understand its reductionist properties. And then I'll come to the central topic of today, the dark matter challenges of the solid state, and I'll tell you a bit about them. And if time permits, and we'll see how it goes, I'll tell you about one topic that really fascinates me at the moment, the collision of two concepts. One, the concept of topology, and the other, the concept of fractalization. Okay? So that's the outline of the talk. Let's see where we get to. Okay, so of course, you folks don't need any reminding of the deep link between the laboratory on the cosmos. And when I was an undergraduate, I lived actually in the staircase that Isaac Newton was supposed to have worked and written part of Principia. And of course, according to the legend, he looked at the falling apple in the orchard during the pandemic, I might add, and thought, well, maybe the force on that apple extends out into the cosmos, to the moon and to the planets beyond. And of course, this idea of the link between the physics and the lab and the physics and cosmos is part of our DNA. And one of the things I wanted to emphasize as part of my talk is it's just as alive today as it was back in the Renaissance. Of course, one area in which it affected physics in the last 50 years was the understanding of gauge fields and their interplay with broken symmetry, and the understanding of how a superconductor levitates, of course, led to the understanding that photons acquire mass inside the broken symmetry environment of a superconductor, but moreover, that we ourselves live in a kind of cosmic superconductor in which one component of the electroweak force is screened out and becomes the weak force that drives sunshine. So this is true today, and I think this is a really important thing to realize. And this energy and this convection of ideas between the lab and the cosmos is really important today, just as it was 400 years ago at the birth of physics. And so let's just remind ourselves of where our field lay 100 years ago, 120 years ago, the early signs of the quantum age. And of course, there were many unanswered questions, despite the singular success of the 19th century physicists. Many things didn't seem to be going right. And they didn't understand why hot things change color, why matter is so hard, why we don't tumble right through the floor beneath us under the influence of gravity, and why does the sun shine? So let's talk about those things. These 19th century mysteries were early signs of a quantum revolution to come. Let's talk about them a bit. Why do hot things change color? This led to the concept of black body radiation and the discovery of the photon, which was, of course, the beginning of quantum mechanics. But understanding this required a huge effort throughout the 19th century. Kirchhoff, Wien, Rayleigh, Boltzmann, Planck, and ultimately Einstein led to this change in viewpoint, okay? And of course, it's epitomized by the black body radiation curve, which of course peaks at this one frequency, which defines Planck's constant. It's when h bar omega is of order kBt. This gives us Wien's law, Wien's displacement law. Okay? And so what about why matter is so hard? Well, that's a very interesting story. And why matter is so hard grew out of the study of something seemingly completely unrelated, the study of atomic emission lines. And this led to the phenomenological idea of the exclusion principle, which Pauli invented to describe atoms initially, and then discovered to his amazement, it actually extends all the way to the wave function of a metal. And here is a picture of the young Pauli. Wolfgang Pauli had during his life a very negative view of condensed matter physics, but he did one thing that was quite singular. He invented the Pauli exclusion principle, and he realized that Fermi-Dirac statistics enabled him to understand the properties of metals, in particular their paramagnetism. This was his quote, writing to Schrödinger, that he was really disappointed that electrons seemed to be fermions rather than bosons. Of course, condensed matter physicists today are disappointed too, in a way, because we can't mention the word Einstein very often when we talk about condensed matter physics. We're talking about fermions all the time. So it is, okay? But why is matter so hard? Well, this really comes from the exclusion principle. When we bring two atoms together, we drive electrons into the antisymmetric states of the bonding orbitals. And it's this increase in the energy of the system that leads to the hardness of matter. Were matter made of electrons that were bosons, it wouldn't be hard at all, it'd be soft. And in fact, there'd be no chemistry either. So it is really important. And of course, this hardcore repulsion then results ultimately from this marvelous mathematical equation that tells us that the fields of electrons and of fermions anti-commute. And it's this anti-commutation that leads to the anti-symmetric wave function and to the hardness of matter. It's a wonderful illustration of how our world is connected to the mathematics that describe the quantum world beneath us. Okay. And lastly, what about the sun shining? And the amazing thing is it shines so slowly. Okay. And Lord Kelvin, 120 years ago, confidently, well, no longer than that, in 1862, confidently estimated the age of the sun to be 20 million years old. And the reason he did that was the only thing he knew was chemical combustion. And this put him into direct conflict with the geologists and Charles Darwin, who had estimated a number closer to 500 million years by looking at fossils. Okay. And so this was another great contradiction. And we now know that the resolution of this problem came from the fact that the underlying physics of the sun is driven by a very slow interaction, the weak interaction. When protons combine and fuse to make deuterons, this is driven by the weak interaction as a very small cross-section. And in the sun, a typical proton waits 9 billion years before it undergoes fusion. Okay. And this is all because of the very short range of the electroweak force, the weak force. And of course, this physics shares in common with the Meissner effect a common mechanism, namely a gauge field acquires mass. In the case of the superconductor, the Higgs particle, as you might call it, is the charge pair condensate. It's not a fundamental particle. In the case of the electroweak, our best understanding so far is that this Higgs particle is actually fundamental as far as we can see at the moment. It's a hypercharged condensate. It has two components. And what it does is it drives the weak force to be expelled on a length scale of about 10 to the minus 18 meters. In fact, in condensed matter physics, we don't call it the Higgs mechanism. We call it Anderson-Higgs mechanism because, in fact, Higgs was directly influenced by Phil Anderson's work. Here is a picture of the two. Sadly, Phil Anderson died in 2020, just last year at the beginning of the pandemic. We are still in a state of mind where we miss him greatly, and we haven't had a chance to have a conference celebrating his life yet. But anyway, so my main message here, this is the paper he wrote on plasmons, gauge invariance, and mass. And this is the paper of Peter Higgs, which we celebrated with a Nobel Prize a few years ago. Okay, so in each case, laboratory-based studies were used to reveal deep new concepts that apply equally to the laboratory and to the cosmos at large. Okay, and so these thoughts stay with us today, and they're the theme of my talk today. Okay, so I want to turn to a second topic now, which is reductionism and emergence. And I want to talk about these two things because one of them's deeply in our DNA as physicists, and that's the idea of reductionism. Okay, and it's the marvelous idea that as we take matter apart to its smallest constituents and then understand the laws and the forces that govern them, we can understand everything. Okay. And of course, this is part of the idea that we can divide matter to its smallest components, the molecule, the atom, the nucleus, the nucleon, the quark, and maybe even smaller, the string. Okay. And this idea of reductionism has been extraordinarily successful. As the late Piers mentioned, atoms, particles, relativity, quantum mechanics, the prediction of antimatter, which came out of Dirac's theory, the discovery of gauge symmetries. These really are a monumental tribute to the power of reductionism. And it's certainly something that we don't want to give up on. Even if we spend our lives creating effective theories, we still believe that reductionism is something we strive for. We don't believe in, as some philosophers do, that there may be effects in nature that can't be reduced to their fundamental components. We believe in reductionism. Okay, Nevertheless, and of course, these expositions such as the late Stephen Weiberg's Dream of a Final Theory, Brian Greene's Elegant Universe, Stephen Hawking's Brief History of Time, the first 3 minutes, they capture the beauty of this discovery, but they also give rise to the false impression that the frontier of science is purely reductionist and that the frontiers lie exclusively at the extremes of scale, okay? And so that's where, and so these are those frontiers: dark energy, gravity waves, the Higgs particle, and perhaps the string multiverse, okay? And you can read about those in these marvelous books, and it's immensely exciting, okay? But that's not the whole story. And that's because of emergence. And emergence is the intriguing idea that as matter comes together, it develops not just a big mess, not just immense complexity, but instead novel properties and unexpected patterns of collective behavior. And of course, a symbol of that might be the snowflake on a cold day fluttering down. It's a tiny emergent crystal of water, okay? A flock of geese is emergent because the geese are not following some master plan, they're just optimizing their air resistance. A levitating superconductor, and of course, life itself, we believe, is an emergent property of nature, okay? And so the philosophy behind this was epitomized in the context of biology by folks like Darwin and others, but it was brought into the physical sciences by Anderson, who wrote this very influential paper in 1967, More is Different. And let me read what he wrote there. He wrote that the behavior of large and complex aggregations of elementary particles is not to be understood in terms of a simple extrapolation. Instead, at each level of complexity, entirely new properties appear. And the understanding of these new behaviors requires research, which he thinks is fundamental in its nature as any other. And it's not just that we want to look at the hierarchical structure of physics, it's that we have to do that if we're to understand and filter things out. Until the beginning of the 19th century, physicists described heat using a different unit to the unit we now use of energy. And that was simply because they didn't know that heat was a form of energy. And the reason for that is that, of course, it's a microscopic form of energy, random motion. And Newton and Leibniz never knew about the conservation of energy because they hadn't understood the principle that heat was a form of random motion. It wasn't until the experimentalists came along in the 19th century and understood that heat was random motion and that you could interconvert it, that the concept of energy came into physics. Okay? And so these two things are connected, emergence and reductionism. Okay. And one more thing, the complexity, we're taught that physics is the very large and the very small. And so from that point of view, a micron is not a very small length scale. Nevertheless, between the micron and the angstrom, a lot of interesting things happen. We more or less understand physics down on the angstrom scale. We can describe the physics of a hydrogen atom pretty much perfectly. And with a bit of a stretch, we can describe a gold atom. Okay. But as we start to put them together, interesting things happen. If we take gold and tin, they're pretty much the same on the atomic scale. Gold, when we put it together, forms a nice crystal and it forms a metal, which is interesting in its own right. But tin, which is much less valuable, does something quite incredible. The electrons start to behave as pairs and they form Cooper pairs. The size of a Cooper pair is about 230 nanometers, just below the micron. Okay. And we understand this physics, but on the very same length scale, of course, we have things that we don't understand. Before I come to that, let me just mention that the solid state physicist has now started to think in a different way. We think of the periodic table as a kind of universe of quantum materials. And we know that when we put electrons together, we don't just get a horrible mixture. Compounds are different to the sum of their parts because of the interplay of the exclusion principle, interactions, and interference, okay? So each compound is a kind of miniature quantum universe with its own types of emergent properties. And the quantum phase transitions that separate the worlds, as I'll say in a moment, can be likened to a kind of black hole in the fabric of the phase diagram. I'll tell you more about that. Okay. And last but not least, here is a self-perpetuating organism, Mycoplasma mycodes. This little guy lives inside your gut. And in its smallest form, the cells of Mycoplasma mycodes are about 250 nanometers in size. So they're the same size as a Cooper pair in tin. And whilst we understand the Cooper pairs in tin, we don't understand in any great detail the emergent properties of Mycoplasma mycodes and the emergence of life, but we believe it's part of that same challenge that stretches between the angstrom and the micron. Okay, so that's emergence. Okay, so let me now turn to the issue of dark matter challenges, because I want to do that. I don't want to belittle the challenges of the great frontiers of physics. I grew up being thrilled by the idea of reductionism and particle physics. But what I do want to contrast is the fact that there are challenges which we may have to put on an equal footing to the dark matter challenges of the very small and the very large. So let's talk about that. Here is a discussion of dark matter itself, and I'm not an expert on it, but my colleagues who work in astronomy and particle physics tell me that 94% of the background mass energy density of our vacuum is unaccounted for. That's a pretty big number. And we believe that 24% of that is in the form of some kind of mobile, but very ephemeral dark matter. And that 70% is a kind of vacuum zero-point energy that causes the universe to accelerate. Some have called that dark energy quintessence. Okay. And it's fair to say that we don't know what either actually is. Okay. And presumably the dark matter problem is connected to the fact that we can't actually understand the origins of the standard model. Okay. So these are undoubtedly a major challenge to 21st century physics that we should put on aside, together with the fact that we don't understand gravity as a quantum mechanical force. Okay. However, there are problems that we have in understanding condensed matter too. And one of those problems is epitomized by the resistivity of the high temperature superconducting cuprates. This is high TC cuprate, one of them that goes superconducting at 37 degrees, but all of them exhibit this property. And it's linear from the lowest temperatures to the highest temperatures. Now, you might remember, if you haven't studied solid state physics, that the resistivity of copper itself is linear. However, it's only linear over a narrow region around room temperature. No one's ever seen, before these materials were discovered, a resistivity that is linear down from the lowest temperatures to the highest temperatures. And what is so amazing about this linearity is that it doesn't seem to notice when the mean free path of the electrons becomes comparable with the lattice spacing, which should be somewhere around here. It continues to be linear, as if the entire concept that was invented for the conductivity of metals by Drude just doesn't work here. Okay. And in fact, we believe that this physics involves the breakdown of our model, our basic model of metals, the Landau Fermi liquid. And here's another challenge that we have, and I'll talk about. This is a material, samarium hexaboride, which is an insulator, but it only becomes an insulator at a very low temperatures, somewhere around 50 Kelvin. And when it becomes an insulator, it does a number of interesting things, one of which is it has an intrinsic resistivity that never quite disappears. And we've been able to understand this using ideas of topology, but it has another property which we are far from understanding. It seems to exhibit quantum oscillations, which are characteristic of a metal, despite being an insulator. Okay. And so these and many other examples suggest the potential for qualitatively new advances in our understanding of quantum matter. And I'd like to expand on that in the next few minutes. That's what I'll do. Okay. And whether we get round to my particular interest in samarium hexaboride doesn't really matter, because I want to emphasize these challenges that we have. Okay, let's look at this linear resistivity. It's not just a property of the cuprate superconductors. And we believe it's connected with the physics of electron localization. So here's a little picture of the periodic table rearranged so that the unfilled shells of the F or the D shells are organized in order of increasing localization. And now you may remember also that as you go from the left to the right-hand side of the periodic table, the unfilled shells, the wave function of the unfilled shells gradually collapses in what is known as the lanthanide contraction. And so interestingly, if you take elements down here, they exhibit superconductivity because the unfilled shells have electrons that are delocalized. But if you take elements up here, the unfilled shell electrons form magnetic moments. And those magnetic moments are very important to modern technology. For example, neodymium is used to strengthen the magnetism of iron, and it's an essential element for the high performance magnets that drive hybrid cars, for example, and modern cars, and also your toothbrush. This is then an interesting thing, because in these two limits, the electron behaves in different ways. On the left-hand side, electrons behave more or less like waves, but on the right-hand side, they behave as localized magnetic moments. And quantum mechanically, we describe these two things very differently. This thing is described in terms of a delocalized band structure. This thing is described in terms of an individual spin operator, which is neutral. Okay. And so what's very interesting is the physics that develops in the crossover between these two regions. And the cuprates are part of that crossover. And there are a number of other interesting materials that lie in the crossover. And so, for example, the recently discovered iron-based superconductors involve electrons that are on the brink of localization. Fascinatingly enough, these actinide systems, uranium, neptunium, and plutonium, also have very interesting electronic physics. Okay, and so they've been the subject of great investigations, not because of their radioactivity, but also because of their interesting properties as quantum materials. Okay, and so electrons on the brink of localization. And new kinds of quantum matter develop at this brink of localization. Okay. And so here's another example of a miniature high temperature superconductor, which also exhibits linear resistivity. This is cerium cobalt indium 5. It has completely different chemistry to the cuprate superconductors, but it also has electrons on the brink of localization, and it also exhibits this remarkable linear resistivity. And so we've seen this kind of behavior now for 20 or 30 years, and it has actually defied the best efforts of the community for its explanation. Okay. But one thing we do understand about these materials is that when we look at their resistivity being linear in temperature, we can sort of fit that into a Drude model of conductivity, where the important thing is the mean free path, or the scattering time, the so-called scattering time. And in all of these systems, when we look at the size of the scattering rate, it's governed by nothing more than the temperature. In other words, the scattering time is just h bar over the temperature. And this scale we call the Planck scale. It's not the Planck length or the Planck mass, it's the Planck time. This is truly scale invariant scattering. And we don't understand why this scale invariant scattering produces resistivity that's completely independent of the underlying physics, the phonons, the disorder. This linear resistivity is completely robust against the details of the underlying lattice. Okay. Many metals saturate the resistivity when they hit the so-called Debye temperature, but the cuprates don't. We don't understand why. One idea is that this is connected to quantum phase transitions and the concept of quantum criticality. And I wanted to spend a digression talking about this, because this is another unsolved problem in condensed matter physics today, the understanding of phase transitions, which are driven not by thermal fluctuations, but by quantum fluctuations, okay, and zero-point motion. So let's talk about that a little bit. I'm going to blow this picture up, okay, and tell you a bit about this material, ytterbium, rhodium-2, silicon-2. It's an interesting material because it's a metal, and it exhibits a phase transition into an antiferromagnetic state somewhere around 0.08 Kelvin. Okay, so this is 80 millikelvin down here. This is a very, very fragile magnet, and a very tiny magnetic field causes the magnetic, the nail temperature to suppress to zero. Okay, so however, this transition here is a classical phase transition. It's second order and is described by what we call a classical critical point. Okay, and until 1960, the physics community thought it had solved the problem of second order phase transitions using the ideas of van der Waals. But they started studying this and discovered that actually there was a whole explosion of things they didn't understand. Okay, and this became known as the classical critical problem. Okay, here is a here is a picture of the phase transition, the specific heat capacity of oxygen at its critical point. And it shows this phase transition, this lambda-like specific heat capacity, which is characteristic of Ising phase transitions. And the community realized at this time that they couldn't explain the exponents of this phase transition. And they realized that that was because they didn't understand the correlations that develop at a second order phase transition, what we now call criticality. One of the major participants in this revolution was Michael Fisher, and he mentioned one of his ideas that he often mentioned was that new insights into physics often come from revisiting areas once thought to be closed, and that's what he did in the early 1960s. He went back to the theories of van der Waals and realized that they don't work, and it led to a revolution in the understanding of physics, and which was fascinating because this revolution involved the use of methods from field theory. Methods from field theory were brought in and used to understand the divergence of the correlation length, the universality of the physics, and the basic idea of classical criticality is that you have an order parameter whose correlation length diverges, and on length scales on length scales less than the correlation length, the correlations have universal power laws, and they forget about the details of the microscopic physics. And so whether you look at a magnetic phase transition or the critical point of water, completely different physics on the short distance, but exactly the same Ising critical exponents at long distances. Okay, and so this is the idea of classical criticality, and it was a 20th century revolution. Okay, a quantum phase transition, by contrast, is a phase transition driven by zero-point motion. In ytterbium, rhodium-2, silicon-2, the order parameter is the staggered magnetization, and it doesn't commute with the Hamiltonian, and so it undergoes zero-point fluctuations. And as you tune up the magnetic field, these zero-point fluctuations become large enough that the TC is driven to zero. Okay, and so the question is, what happens when the time and length scales of zero-point quantum fluctuations diverge? And this is then what we call a quantum critical point. It's a critical point driven by zero-point motion. And so our physical picture of it is that we have a quantum critical matter on length scales up to the correlation length or the correlation time, and that perhaps there's a new universality of the physics on these long length scales and long time scales. Now, we can understand that universality in the simplest case of insulators, but we're very far from understanding what happens when these fluctuations couple to the fermions in matter and give rise to quantum critical fluctuations inside a metal. And so in this particular material, here's the resistivity that you see when you tune it to this quantum critical point. And notice that once again, it's linear in temperature. In fact, it's linear from very low temperatures, from below a tenth of a Kelvin into the millikelvin regime, all the way up to about 10 Kelvin. This is the logarithmic derivative of the resistivity, which hovers around 1 up to about 20 Kelvin. Okay, and so what's interesting is that this quantum critical point produces interesting physics up to very high temperature scales. Okay, going way off this. In my office, that would take me to the next floor, 20 Kelvin. Okay, and so quantum critical points are very different to classical critical points. They affect wide swaths of the phase diagram. And this region here is the strange metal, which we don't understand. Okay. So, yeah, and so this is the region where we have Planckian dissipation. And so one of the thoughts that the community has had is that maybe the modern methods of field theory, 21st century field theory, perhaps the Maldacena conjecture, perhaps the methods of holography will help us solve this problem. Okay. And so that is Planckian dissipation. And there is a link of this Planckian dissipation with high temperature superconductivity. In the cuprates, the iron-based superconductors, and these miniature heavy fermion superconductors, we see this linear resistivity time and time again. Okay. And so these then are some of the dark matter challenges of the solid state that I've shown you here. And I've shown them to you without providing their solution because they fascinate us and we don't have a solution to these problems at the current time. Okay. These and many other examples suggest the potential for qualitatively new advances in our understanding of quantum matter. And these advances involve many new ideas. One of the key ideas that comes in is the notion of entanglement. And so what we're looking at here are new forms of electron entanglement, which involve huge numbers of particles. This leads to the possibility of new kinds of phase transition and also quantum phase transitions, new kinds of broken symmetry. Fractalization is an idea, and an interplay with topology. So these are some of the ideas that are buzzing around. And one of the other points that we realize is that if we do understand these problems, then probably, most likely, there'll be some aspects of them that will modify our understanding of physics in the vacuum itself. And so you could imagine that some of these problems might even be connected to some aspects of the unsolved dark matter problem. For example, the physics of neutrinos isn't understood. Well, we have neutral excitations forming inside quantum matter, which come from a phenomenon we call fractalization. Could they be related? Nobody knows, but it wouldn't be a great stretch. Okay, so having talked about that, I'd like to end my talk skipping over and talking a little bit about these last two aspects, the notion of topology and the notion of fractalization, which are very active topics of discussion in the condensed matter community. And I probably won't have time to do them justice. Maybe I should even stop here, but maybe I'll talk for 5 or 10 minutes on these topics and we'll have a discussion about them, okay? So this is really my punchline. As in the past, phenomena in the lab and the cosmos at large are likely to be linked, okay? And so this is a plea for a more integrated approach to physics, that we actually talk to one another more, that we connect ourselves together between astronomy, between particle physics, between soft and biological matter, because we have a common frontier that we're fighting, okay? Okay, so, but let me now turn to a collision of concepts. This is going to be a more specialized part of the colloquium, and if it looks too technical, please forgive me, I'm only going to spend 5-10 minutes on it anyway. So I'd like to talk a little bit about this notion topology. What the heck could topology have to do with electrons moving through a material, okay? And so the idea here is that the differential geometry of the wave function defines a kind of topology, okay? And this is an idea that's been growing over the last 10 or 20 years, driven by experiment, okay? And it's involved for example, a tremendous revolution understanding the integer quantum Hall effect. The plateaus of quantized Hall constant are due to the formation of a state that has a gap. It's a novel form of insulator, okay? And one of the key ideas that came out of this is the notion of a Berry connection. The fact that in momentum space, there is a kind of field which relates the way the wave functions can be parallel transported around the Brouin zone. And this quantity, this vector potential in momentum space, affects the physics, and its textures are quantized due to the underlying topology. And that's what gives rise to this integer quantum Hall effect, as was first discovered by David Fowler back in 1982. Okay. I should add that the properties of helium-3 are also topological. It has a wave function in which the orientation of the Cooper pairs in momentum space and spin space actually forms a hedgehog. And so the B phase of helium-3 is another topological phase of matter. So when you take the loop around the Brouin zone of this topological Berry connection, it turns out that this thing is quantized and determines the quantum of Hall conductance. Okay. But more importantly, it turns out that these ideas even extend to the understanding of elementary insulators. And this was then the revolution of topological insulating behavior, which involved this huge cast of characters. And once again, involved a community of physicists working together, not just particular individuals. In fact, the Nobel Prize has been given for the first phase of topology, but it has not yet been applied to the second phase of topology. And the guys in Stockholm have a big problem because there's just too many people to put under one prize. Anyway, so what is this idea of topology? Well, in a nutshell, it's the idea that you can kind of wind up the wave function. And so the vacuum and conventional insulators are really adiabatic continuations of one another. And the gap of the vacuum, which is a million volts, and the gap of silicon are adiabatically connected. But in a topological insulator, you get a kind of twist of the wave function, which is induced by an inversion of states in the insulator between the conduction and the valence band. And this band inversion twists the topology. And when it does so, it means that you can't adiabatically go from the vacuum inside here to the vacuum outside there. And the only thing that can happen is that the gap has to close before it opens up again. And when it closes, you get metallic surface states.
Are they going to adjust? Will they do it on every map? Is there a little bit of spice in there? And I think we've seen that, yes, this is not just like econ.
Someone is unmuted. Okay, great.
Yeah.
Okay. So that's the key idea of topological insulators. It means that a topological insulator will then have conducting surfaces, and it actually has Dirac cones on the surface. Okay, and this is the revolution started just 10 years ago. So one of the things that we've been interested in is how this topological revolution interplays with electron interactions. And this is the story of samarium hexaboride. And when I first heard about topological insulators, I remembered this old material. And I thought, well, you know, that could be a good candidate for this stuff. And so this led to a lot of excitement. And then we discovered that we hadn't fully understood the problem and that something else is going on. So here's what we thought at first. This system, here is samarium hexaboride, and here is its resistivity going upwards on a log scale here. If you plot it versus 1/t, you see that it has a nice, let me come back to this in a minute. This thing develops a gap. Okay, so going backwards again, one of the simple models for this system is what is known as a condo lattice. And the idea is the following, is that these local moments in samarium hexaboride have an exchange coupling to the conduction electrons. And this is the model that's called a condo lattice model. It involves mobile electrons and localized moments interacting with spins. And this model looks very innocent, but it actually hides a lot of sophistry. One of the things we know is that, like the problem of QCD, this coupling constant here scales to strong coupling, and it renormalizes And at some point, it becomes so large that you can think of the problem as going to the strong coupling limit, where this is the dominant part of the interaction. So simplistically, and I am being simplistic here, you can think of the ground state of this Hamiltonian when the number of electrons equals the number of spins to be a kind of insulator in which every spin is bound to one electron. And that's called a Kondo insulator. And in a very, very naive treatment, this describes this insulating behavior with appropriate renormalizations, okay? And interestingly enough, even though the band is half filled, the spins behave as spin 1/2 excitations, converting the system to a filled band insulator. And this model is, in some sense, an early example of spin fractalization, because the spins of this Kondo lattice are behaving as if they're electrons, okay? So this then raises the interesting question, what is the interplay of topology with spin fractalization? And we thought we knew the answer to this problem back in 2008. We thought, well, look, in fact, people have even seen a resistivity plateau below 3 Kelvin. Maybe this is topological surface states. And this led us to write this paper in 2010. Takimoto followed us shortly afterwards, suggesting that this is a topological insulator. And the idea was that the D bands of the conduction electrons, if you think about this in a weakly interacting point of view, cross through the F bands and form a surface states. They cross actually at 3 points, and the X point in the Brand zone, and so you should get 3 Dirac cones on the surface. So we contacted our experimental friends and said, you know, you should do some experiments. And the first experiments were extremely encouraging. They saw the fact that the Hall constant came from the surface. They also found with ARPAs these Dirac cones that are on the surface, and there were 3 of them, and they could even understand this on different surfaces. Everything looks really good, and in fact, they could even find a way of measuring the bulk resistivity, which, in contrast to the surface, the surface shorted resistivity drives up through many decades of temperature. Okay, this is an extremely good bulk insulator with conducting surfaces, and so it looks like it's a topological insulator par excellence. Okay, so great, except, but unfortunately, that's not the whole story. And there are many strange aspects of this material which suggest that this is not just an insulator with topological behavior and conducting surfaces. And these are some of the conundrum features it has, which I'll very quickly show you. This system has a large linear specific heat, which we normally consider to be the property of a metal with a Fermi surface. In fact, lanthanum hexaboride used to be of technological importance. This is the cathode that was used in all our old-fashioned TV screens, which created electron guns. It's very, very good. It's a very, very good emitter, but its specific heat capacity is much, much smaller, its linear part, than samarium hexaboride, even though this guy is a metal, this guy is an insulator. They have exactly the same crystal structure. The samarium has F electrons, the lanthanum does not. This system also doesn't exhibit a clean gap in its conductivity. It shows a lot of AC conductivity far in the terahertz. Terahertz you might think is pretty rapid, but this is a frequency scale well below the gap of this system, and yet it's still conducting in the bulk. Why? Okay. And how can it be conducting the bulk according to an electromagnetic probe? This is optical conductivity, and yet such a good insulator from DC probes. Is it that the conductivity plummets to 0 at low frequencies, or is something else going on? This is its thermal conductivity. It does exhibit a thermal conductivity in a magnetic field. And last but not least, horror upon horrors, it exhibits quantum oscillations. And so what are these plots here? These are the plots showing the determined Fermi surface of this system as a function of angle by following these oscillations measured in the torque, oscillations of the torque of the system in a magnetic field. And so these are oscillations that we believe are associated with the bulk susceptibility. And the fact that we see this temperature dependence here tells us that we have something resembling fermions, which have Landau quantization. Okay. And so this is what the experimentalists inferred from their experiments. Okay. And yet they never saw any oscillations in the surface conductivity. In fact, they never saw any oscillations in the resistivity at all. So this is very unusual. And it's led to a big conundrum. It's led to the experimentalists claiming that there's a neutral Fermi surface, which resembles that of lanthanum hexaboride. But then you say, well, how can a Fermi surface be neutral and exhibit Landau quantization? Okay. And that's the conundrum of this system. Okay. On the one hand, it looks like a topological conduit insulator. But on the other hand, it has many properties that suggest there is a bulk Fermi surface. And when you get paradoxes like this, they're a very good place to hunt for new ideas. Now, I could stop my talk here, but I'll just very quickly tell you about the connections with fractalization. We did start 5 minutes late, so that's not so bad. So could there be two competing insulating phases in this system? Could there be one insulating phase that is a topological insulator and another one which behaves in this bizarre way? And the other aspect to it is that in this system, on the left-hand side here, the F electrons are basically localized. And so we have to think of them as a spin that has become fractionalized as an electron. So could it be that the fractalization changes in going from here to here? We came up with a theory which suggested that there could be a new kind of fractalization. I'm using this word fractalization. Let me remind you of fractalization. So we made a hypothesis that there's a Majorana Fermi surface in this material. Why? So what is fractalization? These are excitations that emerge with fractional quantum numbers. Solitons in polyacetylene is a famous example from the 1980s. The anions of the fractional quantum Hall effect, these are particles which form inside the fractional quantum Hall effect with fractional charge and fractional statistics. Okay, they have a charge which is E divided by an integer, an odd integer. Okay, and finally, in a one-dimensional Heisenberg chain, we know that when we flip a spin, we create two spin-ons, two spin 1/2 excitations. And the way we think about it is that we flip a spin to create what should be a magnon, but that magnon breaks up into spin 1/2 spin-ons. These are the main walls in a very simple picture. Okay, and most recently, Kitaev has shown in an absolutely fascinating model, the Kitaev honeycomb model, that spins fractalize into Majorana fermions. And in fact, in this model, the reason the spin can fractionalize, it's very, very subtle. We know that in quantum field theory, we have a Fock space, but when a spin fractionalizes, it creates an emergent Fock space. And just as Dirac realized that quantum electrodynamics required supplementary conditions, in these systems, there's a supplementary condition which defines the slice of that Fock space that describes the physical system. And there is an emergent gauge field in the Kitaev honeycomb lattice. And so this led us, a Majorana fermion is a kind of the real part of a regular fermion. This led us to wonder whether in our localized moment systems described by this Condor lattice model, whether we could have a new kind of fractalization. In the Condor lattice, we know that the spins behave as electrons. They fractionalize into electrons and they expand the Fermi surface. Okay, and so could spins fractalize into Majorana fermions in a Condor lattice as they do in the Kitaev model? Okay, and if they did that, then something interesting would happen. Conduction electrons can be thought of as a spin up and a spin down fermion, and a spin up and a spin down fermion can be thought of as 4 Majorana fermions. And so if the spin fractalizes as a Dirac fermion, they can be connected up very naturally. And that's what we call a Condor insulator. But if the spin fractalizes as a Majorana fermion, like so, then it can be treated as 3 Majorana fermions. And when it's 3 Majorana fermions and the electron is 4 Majorana fermions, there's a mismatch. And so what then happens is that one of the electron Majorana components gets left behind. There's a gapless excitation. And this gapless excitation doesn't know whether it's an electron or a neutral fermion. It doesn't respond to a chemical potential change, but it seems to respond to a transverse vector potential. And it forms a kind of, well, we don't know what to call it. In a way, it's a kind of failed superconductor. From another point of view, it's an insulator. And from another point of view, it's a half metal because it responds to transverse vector potentials, but not longitudinal vector potentials. It's what you might call a transverse metal. And we're exploring this idea in detail. This transverse metal can have de Haaspan-Alphen oscillations. Here's a plot from our model. This is what happens if you have just a regular Fermi surface. And these are the energy levels we get in our mean field theory of this transverse metal. It looks like a kind of failed superconductor. And we followed this theory to the end. And we discovered that although this superconductor has a Meissner stiffness, it can't form any stable vortices. And so you can't wind up the phase of this superconductor. You can't create a persistent supercurrent. And instead, the supercurrent unravels on a timescale that makes it resemble an insulator. That's the theory we put together. We've had a lot of fun with it, but I want to mention that it's not worked. Because it turns out that in the model, as we currently got it, we find that below a certain critical field, our failed superconductor starts to exhibit a Meissner effect. We estimated this Meissner scale, and we thought we were being very safe by estimating it to be below the Earth's magnetic field. But in fact, you can easily exclude the Earth's magnetic field and test its properties. And guess what? It doesn't become diamagnetic. And so our theory, despite its beauty, hasn't worked. But that's the way physics goes. You make a theory, it doesn't necessarily work, and then you try again. We haven't given up on this idea. We think that the version 1.0 has failed, but that doesn't mean it's not good for the future. And so here are my conclusions. First, the specialized conclusion about samarium hexaboride. It's an orbital diamagnetic insulator with undamped de Haaspan-Alphen oscillations and a bulk specific heat. It seems to have some second phase, a phase that is neither a metal nor an insulator, but something in between. And we're starting to call it a transverse metal. A few other things, a Majorana fractalization of spins may allow for competing phase with a neutral Fermi surface. But my more general conclusions, my broader conclusions, are the ones that I really want to leave you with, because that was my specialized conclusions. History teaches us that physics in the laboratory and the cosmos are often intertwined. And we may be interested in emergent properties of matter, but we need to learn the fundamental properties of field theory to study them. And likewise, we may be interested in the reductionist properties of the vacuum, but we may have to be careful about the emergent properties of vacuum, which we have to understand before we can get there, okay? And so in that sense, the solid state maybe has some interesting lessons to us. The dark matter challenges of the solid state, there's a potential for qualitatively new advances in our understanding of quantum matter. And if we understand quantum matter in a better way, we might discover some new universal properties about quantum mechanics that we've been missing. And finally, samarium hexaboride, it's an old mystery that brings together ideas of topology and fractalization, and we're still actively working on it. Thank you very much.
Thank you very much for your talk. I think we have questions immediately. So Professor Luis Foix has a question.
I haven't been looking at the chat.
No. I've been looking at the chat.
Okay. Yeah. Okay.
Yes, please.
So thanks. So thanks a lot, Piers, for this great talk. I really enjoyed it very much. And I think although most often we hear a lot about high temperature superconductivity, I think you have made a great point that the real challenge is this linear resistivity behavior. And I was wondering, what do you think that is there any space for phonons, in particular chiral phonons, to have anything to do with this?
Well, so phonons do produce a linear resistivity, so long as you're above the Debye temperature. Okay. And typically they maintain that linear resistivity until the point where the mean free path starts to approach the lattice spacing, at which point typically the resistivity saturates. Okay. So the problem with this system is that, first of all, we know what the Debye temperature of the phonons is, and it continues to be linear below that scale. But equally badly, the resistivity doesn't saturate at high temperatures. And so people call the high temperature behavior a bad metal and the low temperature behavior a strange metal. But actually, observationally, there's no difference. It just goes straight through. And it's a fascinating question. If the lattice didn't melt at 1,000 Kelvin, would it go on up? And optical conductivity suggests it would in the frequency scale. So this is really scale invariant physics, and we're a little bit at a loss as to what's going on. There are other aspects to it that I didn't have time to talk about. It turns out that the Hall constant isn't constant in this metal. One of the great properties of metals is they have constant Hall constants, and it turns out that's due to a very remarkable cancellation between the transport times for longitudinal conductivity and the rate at which a transverse current decays, which is kind of determined by the it is also determined by the transport time. But in these systems, it's as if the decay of the transverse currents is governed by an entirely different time scale to the decay of the longitudinal currents. And as a result, in fact, you have a t squared relaxation rate of the transverse currents and a t linear of the longitudinal. This makes us begin to wonder whether the transverse physics might be metallic and the longitudinal might be different, might be Planckian. And so one of the reasons we're fascinated by ceramic toroid is it might be an extreme version of that, in which the longitudinal physics is insulating and the transverse physics is metallic. So it might teach us something about the cuprate. So I think the community is divided, that we'd love to find a conservative Occam's razor description of the strange metal phase. And if you could make it work with phonons, it would be great. And we all settle for that. But I think there is sufficient strangeness in its behavior that we're sort of forced out of our comfort zone and have to think about other explanations, which at the moment are radical, but maybe in the future will become the new conservative.
Great, fascinating, really. Thanks.
Thanks. Are there other questions? I have one. When you were discussing the quantum critical point, as I understood, you said that the influence of this critical point was quite large, in the sense that do you have an understanding of why it has this influence not so close to the critical point?
Yeah. So let me remove the pin. That's better. Yeah. So in broad brushstrokes we do, and that's because temperature plays a very different role in a quantum critical point. In a classical critical point, it tunes you closer and closer to the phase transition, and so only when you're very close to the phase transition do you see anomalous behavior. But in a quantum critical point, temperature is not the tuning parameter anymore. It's some other thing. It's the magnetic field, it's the pressure, and other things. And so what does temperature do? Temperature plays a very curious role because, as you know, the thermodynamics of quantum matter is like a Euclidean field theory in one extra dimension. And the dimension of that extra dimension is the imaginary time direction, we call it, right? It's Euclidean time. And the extent of it is is exactly the Planck time, h bar over kBt, okay? And so what we do when we do finite temperature quantum field theory is we use Matsubara frequencies. We take a world that is periodic or anti-periodic in the imaginary time, and we get all of our statistical mechanics properties out of it. But what this means is that the Planck time is a cutoff on the quantum critical behavior. And so if you had some kind of universal quantum critical behavior, if you were below the upper critical dimension, then we would expect that h bar over kBt would be the only time scale in the problem. It would be the correlation time of the physics. Right? And so if there were some kind of universal physics at that quantum critical point, then we would expect the transport time to be the Planck time. Okay, and the other reason that you get this broad swath of quantum critical behavior is that so long as that Planck time is long and much longer than the cutoff timescales of the underlying physics. In other words, so long as kBt is much smaller than the short distance, the ultraviolet cutoff in the problem, you'll have quantum critical behavior. And so when we see this quantum critical behavior going up to 20 Kelvin or 10 Kelvin, that's because we're still well below the ultraviolet cutoff for that particular quantum critical physics. And so at some length, in some sense, the fact we see these beautiful linearities makes us suspect that there is a quantum critical point there. And that in the case of the cuprates, it goes up to 1,000 Kelvin because the relevant scale to this system is above 1,000 Kelvin. But what the detailed physics is, what the reductionist description of that universal physics is, we don't know at the moment.
Okay, I understand. Thanks. Are there other questions?
I have a comment.
Yes.
Could you please expand on the idea of renormalization group approach for highly correlated systems? I haven't heard. I heard a lot about renormalization during the 70s and 80s, but then it sort of stopped a little bit. I don't know.
So it's kind of taken into two parts. So quantum criticality can be understood in a very simple way in the simpler systems by just imagining them as one additional dimension in the stat mech problem. So that when you do system mechanics of an Ising model, for example, of course you do it. It might be a three-dimensional Ising model, but when you want to do the quantum Ising model, you have to add the additional dimension of time because you have to integrate over all configurations in space and time. And so if you've got a system which is relativistic at its quantum critical point, you can use all the standard methods of renormalization group to describe that problem. Now, what happens, unfortunately, is that typically, so this was done by Hertz in the 70s and the 80s, and one of the things they discovered was that time doesn't count as one dimension, but counts as z dimensions. There is a dynamical critical exponent called z, which modifies the physics, and a lot of work was done on this. The reason I'm mentioning this is that in the case of metals, it turns out that the dynamical critical exponent of, say, a ferromagnet or an antiferromagnet is more than one. It's 2 for an antiferromagnet and 3 for a ferromagnet. And so the quantum critical physics of, say, a three-dimensional ferromagnet is predicted to have an to have an effective dimensionality, which is 3 plus z, and z is 3, so 3 plus 3 is 6. And then it's above the upper critical dimension, so you shouldn't see interesting physics. And yet experimentally, the physics looks interesting. It looks as if we're below the upper critical dimension. And so the problem is that the simple extension of stat mech to higher dimensions, which should describe quantum criticality, doesn't seem to work in metals. It seems to work in insulators, but not in metals. And so there's been a whole effort to do RG around a Fermi surface, and it's led to mixed results.
And concerning the first part of your broader conclusions, it brings to mind the famous poem by William Blake, "To see a world in a grain of sand and a heaven in a white flower."
That's a wonderful quote. Yes, I agree with you. Thank you. Thank you, Mario. Maybe a good point to end, actually.
Yes. Yes. Excellent. So thank you very much Piers. It was a wonderful talk, and it was very interesting. So,
it was
thank
great
you.
to come down and visit you, if only fleetingly by Zoom. Next time, I hope I can come in person.
Yes, we hope so also.
Yeah. Okay. Thank you,
Okay.
Rodrigo. Thank you, everyone, for coming.
Thank you very much.
Thanks.
Thank you.
Okay. Bye-bye.
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 Thanks.
Bye.
Chao, chao.
Chao, chao, Rodrigo.
Chao.